Share the screen. No questions. So today we're going to finish our lesson, and it will be Chapter 7, the control of microbial growth. We had already started that lesson. Please note that the worksheet to Chapter 7 is not due on Saturday. I've got it due on Wednesday. Now, why did I say Wednesday? It should be due on Thursday. Let me take a look at that. Come on. I'm not able to get it. I don't know what's wrong here. All right, there I got that. That was a hard way to do it, though. We're almost at the end of the term. Any comments about that? We're on our last lesson. No comments. Come on, will you stop moving? There we go. Let's make that Thursday. And I guess I should change this. All right, so the worksheet to Chapter 7 is due Thursday. On Thursday, we will have a review for the final. Today, you're just working on your unknown work. I will be at the lab from 6:30 to 6:45. So if you have any questions, please log on between 6:30 to 6:45. On Thursday, I don't know if there will even be a lab, but we'll see. Your unknown project is due this Saturday at 11:59 p.m. Any questions about any of that? All right. Let's go on to the lesson. So we were talking about the terminology of controlling microbes. And let's go on with some further terminology. Sepsis refers to microbial contamination. Asepsis is the absence of contamination by unwanted organisms. So when we give you media, hopefully it has been with asepsis. And that obviously would be if you were really going into the lab. In the virtual lab, I pretend I'm giving you media. Aseptic techniques are important in surgery to minimize contamination from the instruments, the operating personnel, the patient, and the air. So we use aseptic surgery today to minimize the patient getting an infection from the surgery. Any question about any of that? All right, not hearing anything. Let's move on. Some actions of microbial control agents. Antimicrobial agents kill or inhibit microbes by doing one of three things. They can alter the membrane permeability. If you damage the plasma membrane, either the lipids or the protein, you can cause the cellular contents to escape and, well, it'll interfere with normal cellular metabolism, and the cell will then die. Any questions about that? Can I get confirmation that you guys are hearing me?
I can hear you.
Thank you. The second way that antimicrobial agents can kill or inhibit microbes is damage to intracellular proteins. If you denature proteins, especially the enzymes, such as by targeting the disulfide bridges or the hydrogen bonds, you interrupt their function. And if the proteins aren't functioning, the cell will die. A simple way of doing that, of course, I guess alcohol does more than just denature proteins, but expose cells to alcohol and you'll denature the proteins. The alcohol will also dissolve the cell membranes, and that will kill the cells too. So I guess alcohol actually works on both 1 and 2. And then the third way you can kill or inhibit a microbe is by damaging their nucleic acids. This often results in cellular death. If you give a cell too many mutations, it will likely die. And of course, the easiest way to understand how to damage DNA is expose cells to radiation, either to UV light in the sun or to something like X-rays, and you'll damage the nucleic acids. Any question about any of this? The three ways that antimicrobial agents kill or inhibit cells. Let me give you an example of membrane permeability. Polymyxin B damages the cell membrane, actually any membrane. It puts holes in them, and that would be an example of altering the membrane permeability. I gave you alcohol for denaturing proteins. You could also put the cell in too strong of a saline solution, and that would damage the proteins. Or the third way, radiation to damage nucleic acids. There are physical methods that we have for controlling microbes. You can heat microbes, you can filter them, you can put them at low temperature, which that may not kill cells, but will prevent them from being metabolically active. You can put cells under high pressure, you can desiccate cells, you can put cells under osmotic pressure, and then you can put cells under radiation. These are physical methods for controlling microbes. We will talk, after talking about physical methods, we'll talk about chemical methods for controlling microbes. So you can control microbes both physically and chemically. So let's talk a little bit more about heat. All methods of heating kill microorganisms by denaturing proteins and enzymes. Though if you have high enough heat, such as flaming and incineration, you literally turn the cells into char. And that, of course, kills the cells. And they'll die before they ever become charred, but no point there. Wet heat, such as boiling, And autoclaving and steaming are one way we can kill cells. And it is very effective. We'll talk a little bit about that. The other heat is dry heat. When we bake things, that's using dry heat. But also flaming and incineration use dry heat, although flaming and incineration use very high temperatures, and so they kill cells fairly quickly, because when you put something in the flame, the cells literally burn and become char, and they'll die very quickly. Whereas when you bake things, it takes longer for the cells to die. Moist heat denatures, coagulates the proteins and the enzymes. Boiling liquid, like something at 100 degrees Celsius, or flowing steam, kills all vegetative bacterial pathogens. It kills most viruses, fungi, fungal spores within about 10 minutes. So all you need to do is boil your food for 10 minutes and you'll kill most things. Often the cells die much faster. Like E. coli will die long before you get the water boiling. Just a hot temperature. Don't ask me what temperature E. coli dies at, but it dies before 100 degrees C. However, boiling doesn't kill everything. Endospores and some viruses take longer to destroy. Some endospores can survive 20 hours in boiling water. So endospores are very resistant to heat. You have to be very high temperature before you start killing endospores. Or you expose them to a very long time of heat, like boiling water. The endospores will die over time. It's just they die slowly. So reliable sterilization by most heat requires temperature above boiling. How is this achieved? By using an autoclave. An autoclave, if you do not know, is like a pressure cooker. You're cooking, or you're treating something with steam under pressure, and it's very effective at killing cells, including endospores. The increased pressure raises the boiling point of water to much higher temperatures than can be achieved otherwise. Steam at 15 pounds per square inch pressure and temperature at 121 degrees Celsius is most often used in an autoclave, and that will kill everything in 1 liter in 15 minutes of autoclaving. Any question about that? If you were to attend a real microbiology lab, all the media you would be given has been autoclaved. Sterilization of a surface by steam requires that steam directly contacts it. So steam can also kill things. Steam is going to be a higher temperature than boiling. You make steam at that, and then you heat it up, and then you apply the steam on something to sterilize it. And to sterilize it, the steam has to directly contact the surface. Of course, anything underneath the surface may not be killed if the surface stops the steam from coming in and stops the temperature from getting there. But it will sterilize the surface. Any question about any of that? Okay? So autoclaving even kills endospores after 15 minutes and 121 degrees temperature and 15 pounds per square inch of pressure. And that's why the media in your lab is almost always sterile. Only if some mistake has happened and it got contaminated would growth grow in it. Pasteurization was something that was started by Louis Pasteur in 1857. You do not need to know the year that Pasteur did this, and it's sort of like when I was talking about the history of biology. You don't need to know the year, but you should know that Pasteur started pasteurization, and of course that's a term that came out of his name. Pasteurization reduces the number of spoilage organisms in the pasteurized item. It kills generally all pathogens, but it does not kill all microbes. It's mild heating, sufficient to kill organisms that cause spoilage. The mechanism is by denaturation of proteins and enzymes. However, thermoduric organisms can survive pasteurization. These are organisms that are mesophiles, but they are heat resistant, at least for a short period of time, and they can survive pasteurization. So pasteurized milk, or anything that's pasteurized, is not sterile. What has happened is we've reduced the number of spoilage organisms and killed the pathogens. But there are organisms in there. And that's why pasteurized milk does have a shelf life, even if you don't open it and you leave it in the refrigerator. It does have microorganisms in it, and it will eventually go bad. It's much longer, though, how long it'll last, than compared to something like raw milk. I'm sure nobody has ever gotten that because they don't sell it anymore in almost all the states in the United States. There's two treatments for pasteurization. You can treat the item, which is usually liquid or air, and the most commonly pasteurized item is milk, but beer is also pasteurized and a few other items. You can treat the item at 63 degrees Celsius for 30 minutes, or you can treat it at 72 degrees Celsius for 15 seconds. Most milk today is treated at 72 degrees Celsius for 15 seconds. There is another treatment that you can see that is used with milk, and it's treating the milk at 140 degrees Celsius for 1 second. It's called ultra high temperature milk, or UHT, and the milk is actually sterilized at 140 degrees Celsius. Remember, 100 degrees Celsius is boiling water. So it's treated at 140 degrees Celsius for 1 second. This milk does not require refrigeration, at least until you open it. And you can see it on the stores in a container at room temperature. Until you open it, that milk does not need to be refrigerated. Once you open it, bacteria can fall in from the air, and you should discard it after about a week in the refrigerator. Any questions about pasteurization or ultra high temperature milk? All right. The point is that liquid heat is pretty effective at treating items or sterilizing items. That's not the case with dry heat. For example, this cat climbed into the oven. Obviously, that cat is alive. Any questions about that? Another example of dry heat is not as efficient at transferring the heat and killing microbes is, I know you've all put your hands into a hot oven to remove the container. Obviously you use gloves or something, but the point is you can put your hands into a hot oven. In fact, I had kids when I was taking a field trip of middle school kids. They actually walked through an oven, meaning that short-term exposure was fine. Let me see. An example of wet heat is when something is boiling, you cannot put your hand through the steam. It will burn you right away. Another example that wet heat is more efficient at transferring the heat and killing microbes than dry heat. Some examples of dry heat are, of course, baking, shown here, killing by oxidation, and then flaming and incineration, which are really a very high temperature, and that's killing by charring. To sterilize items by baking, you need to place the item in an oven at 170 degrees Celsius for 2 hours. And that doesn't kill endospores, but that will kill bacteria and fungal spores and fungi and stuff like that. And for wet heat, like I said, we can kill almost everything except for endospores with only 10 minutes of exposure to wet heat. And we're talking about boiling water. Boil things for 10 minutes. So wet heat is more efficient than dry heat at killing microbes. Any question about any of that? Another method for controlling microbial growth is filtration. You do this with liquids or gases. You filter the liquid or the gas through a filter. The pores in the filter allow the passage of the liquid or the gas, but not the microbes. And then the stuff below the filter is sterile. This is very useful for sterilizing liquids, especially liquids that would be altered by heating. Some examples of filtration are various juices, Coors beer, if you're familiar with that beer. They don't pasteurize that beer, and that's why it tastes a little different. They filter it. Vaccines are often filtered. Filtration is not usually done with milk. The large fat molecules, or the globules of fat, and the large proteins of milk would clog the filters, or clog the pores of the filter. And so we don't usually filter milk. Any questions about filtration? All right, another method, a physical method for controlling growth, microbial growth, is to put the item at a low temperature. Low temperature inhibits microbial growth. Refrigeration from 0 to 7 degrees Celsius is an example. Most refrigerators are set at 4 degrees Celsius. This slows the metabolic rate of the microorganism so that most of them cannot reproduce or synthesize a toxin. The psychotrophs, though, live at this temperature, and they do reproduce at a rate of 3 times per day. So they will reach numbers of greater than 2 million within a week, and then cause food spoilage within a week. And that's why when you have food in the refrigerator, it should be tossed after about 1 week. Any questions about that? And when I'm talking about food in the refrigerator, I'm talking about normal food. If you have a high salt concentration or high sugar concentration or a low pH, that food can last much longer than a week. A perfect example is ketchup, which actually has high salt, high sugar, and then a low pH. And if you don't know, a bottle of ketchup can last easily 1 year in the refrigerator. And in fact, my mother and I had a bottle of ketchup in our refrigerator, and I looked at the expiration date, and it was 2 years since we opened it, and almost 2 years since the expiration date. And I said, Mom, we should probably give this to my brother Mike, her son Mike, because he uses ketchup, and we don't really use ketchup. That's why it was sitting in our refrigerator for 2 years. And we gave it to him, and he used it up, and I don't know, maybe a week. He uses ketchup on everything, so the ketchup didn't last too long, and he's still alive. You might have noticed that I made a comment that the ketchup was in my mother and my refrigerator. When she became elderly, I moved in to take care of her, and that lasted for about 5 years. Of course, she died. She's dead now, but that's what I was talking about. All right, so refrigeration slows the growth rate of bacteria, but does not stop the psychotrophs. It does stop the mesophiles, but it does not kill the mesophiles. Freezing at temperatures below 0 degrees Celsius stops metabolic activity. It doesn't necessarily kill all microbes. You'd have to have a, what do they call that? Finicky bacteria, and there's another term for that. You'd have to have a bacteria that's pretty finicky, not very tolerant to temperature change, to die out at freezing. But some species of bacteria do die at freezing, and all species of bacteria, maybe some of the cells die. Of course, endospores, nothing's going to die, but a vegetative cell, about 50% of them will die upon freezing and then thawing. And that's due to the ice crystals forming in the cells, killing even some of the bacteria, but not all of the bacteria. And I'm talking about slow freezing in like a home freezer. I'm not talking about freezing in liquid nitrogen. The ice crystals that form, like I said, kill some bacteria, and it does kill all parasitic eukaryotic species. So if you want to get rid of a eukaryotic parasite, all you need to do is freeze the food, and all of the eukaryotes will die. Any question about any of that? Okay. Like I said, freezing does not kill all bacteria, and in fact, most bacteria, 50% of the bacteria will survive the freezing and the thawing, and so you should not eat raw food that has been frozen, like raw meat. All right, the next method of microbial control is high pressure. High pressure transfers the pressure evenly throughout a liquid, killing the vegetative bacterial cells. High pressure does not necessarily kill endospores. Most endospores are resistant to high pressure, but the high pressure does denature proteins and alters carbohydrates, which kill vegetative bacteria cells. We use high pressure to preserve the color, the flavor, and the nutritional value of things like juices, where heating would usually change the taste. And so juice is one of the things which is, well, sometimes treated by high pressure. Sometimes it's treated by high temperature, and sometimes it's passed through a filter. Okay? If the juice tastes close to freshly squeezed, it is either treated with a filter or with high pressure. If the juice tastes something different than freshly squeezed, then it is treated with a high temperature. And I can't give you any examples because I don't know which brands treat it which way. I just don't know. And there's a little joke about high pressure changing things. We have two lumps of coal, a mother and the baby lump of coal, and they say, your dad's been under a lot of pressure lately, and he's changed into a diamond. Coal under high pressure and high pressure and high temperature can change into diamond. Desiccation and osmotic pressure can also be used to control microbial growth. Understand that both desiccation and osmotic pressure can stop microbial metabolism, but it does not necessarily kill cells. In fact, if the cells have endospores, the desiccated or the high pressure treated, osmotic pressure treated cells, the endospores can remain viable for years. An example of desiccation is something like dried fruit. You can keep that easily for a year and it doesn't spoil as long as it remains dry. The resistance of the bacterial species to desiccation varies tremendously with the species. Something like E. coli is pretty sensitive to desiccation, and it does die. I don't know how quickly it dies, but most cells die within a day of E. coli if you desiccate the dried fruit. So if you have dried fruit and it's been around for, let's say, a month, you're not likely to have E. coli alive on it. However, endospores would remain viable for years, decades, millennia, meaning endospores are not killed by desiccation or high osmotic pressure. Some other examples of desiccation and osmotic pressure is molasses. High osmotic pressure, high salt, high sugar causes plasmolysis, and then the water leaves the cell, the plasma membrane pulls away from the cell wall, and you can actually see the plasma membrane now, and it will shrink. And like I said, some cells die very easily under osmotic pressure, and that would be something like E. coli. Other cells like Staphylococcus aureus are much better at surviving desiccation and osmotic pressure. How good is osmotic pressure at preserving food? we had a bottle of molasses that I figured was 20 years old. And it was so old that it didn't have an expiration date on it. But we figured it was at least 20 years old. And I took the molasses and made my father molasses candy out of it. And he ate it and was perfectly fine after eating it. He really enjoyed it. And that bottle of molasses stayed in my mother's kitchen for 10 more years and had no spoilage after 30 years. After 30 years, Mother finally decided to throw it away because she never used molasses. And I, of course, never used molasses either, so we threw it away. But it was good after 30 years. Any question about any of that? All right, another physical method for controlling microbial growth is radiation. Radiation damages DNA. And I'm talking about ionizing radiation or UV light radiation. Because, strictly speaking, all of the wavelengths of the electromagnetic spectrum are radiation. But when we're talking about radiation, we mean things like gamma rays, X-rays, and UV light. Visible light, we don't usually consider that radiation, as well as infrared, microwaves, and radio waves. Those are not considered radiation, but they are part of the electromagnetic spectrum. Ionizing radiation, such as X-rays, gamma rays, and electron beams, they have a short wavelength, and they ionize molecules in water, producing ions and hydroxyl radicals. And then these molecules bump into other organic molecules in the cell, damaging those molecules. Especially when they bump into DNA, they can cause mutations. And if you get too many mutations in the cell, you'll kill the cell. Any question about any of that? Ionizing radiation can be used to preserve food. Backpackers will frequently get ionized food, and you can see it on the store. It has a very long shelf life, as long as it's sealed. And at room temperature, it lasts a long time because the radiation kills all the microbes in it. Some pharmaceuticals are treated by radiation, and then some medical supplies. Non-ionizing radiation, which is ultraviolet light or UV light, is also good at killing microbes. The difference is obviously the wavelength, but X-rays and gamma rays can go through the item, killing microbes throughout the entire item, which is treated by ionizing radiation. Ultraviolet light only sterilizes the surface. So when you treat something with UV light, only the surface is sterilized. Things underneath the surface, which if the surface blocks the UV light, will not be damaged by the UV light. Any questions about any of that? UV light damages DNA by creating thymine dimers. Two thymines, which are next to each other, when they're treated by UV light, will get a dimer, meaning two covalent bonds between the thymines. And then these thymines will not pair with their complementary base, which is A, in the second strand of DNA. That causes a bubble in the DNA. And this thymine dimer will stop DNA replication and DNA transcription, meaning the polymerase, either the DNA polymerase or the RNA polymerase, when it's running down the DNA, it'll be stopped by this thymine dimer. It can't continue. Any questions about non-ionizing radiation or ultraviolet light? Microwave radiation, which is on the opposite side of ionizing radiation from visible light. So microwaves are on the opposite side of visible light. They are not particularly antimicrobial. However, microwaves do heat things, and the heat itself will kill microbes. But the microwaves directly are not particularly antimicrobial, meaning they are slightly antimicrobial. They're just not very good at it. But the microwave will heat what we're microwaving, and if you heat it enough, you will kill the microbes. If you don't know, when microwave radiation heats something you're heating, like, I don't know, a potato, the microwave is converted into heat, which is another form of energy. And then the heat can kill the microbe. All right, any questions about any of that? So this table is giving us the physical methods for microbial control. You don't need to memorize this table. You should know the different methods. You should know a little bit about the comment, like dry heat, effective, wet heat. It's actually more effective. And that's a continuation of the table, talking about all the things we talked about. All right, let's move on to the chemical methods of microbial control. There are few agents that actually achieve sterility. Most of the chemical methods for controlling microbes only decrease the microbe numbers to a safe level or remove the vegetative forms of the pathogen from an object. They do not sterilize the agent which is being treated by the chemical antimicrobial agent. So when you disinfect your toilet, you don't sterilize it. You're just reducing the microbes on the toilet. And it's reducing it to safe levels, by the way. All right, the principles of effective disinfection. Disinfection is the destruction of vegetative pathogens. And there are various factors related to how effective the disinfection will be. So when we're treating something with a disinfectant, destroying the vegetative pathogens, the concentration of the disinfectant will be one of the factors related to how effective the disinfection will be. The time of exposure obviously will be related to how effective the disinfection is. The pH will be related to how effective the disinfection is. And the presence of organic matter will affect how effective the disinfection is. In the first two, the concentration of disinfectant and the time of exposure to the disinfectant, generally the more, the better. So if you concentrate the bleach at higher in concentration, it'll be a better disinfectant. And if you use longer exposure time, you'll get more cell killing. With pH, generally, more acidic pH is better at killing cells than a less acidic pH or a neutral pH. A neutral pH doesn't kill many cells. The presence of organic matter can inactivate the disinfectant. So generally you want the absence of the presence of organic matter. The trouble is, in clinical situations, you almost always have organic matter around. Any question about any of that? Let's talk about bleach with all of these since I started with bleach. Generally, if the bleach is more concentrated, it'll be a better disinfectant, meaning it'll kill more cells. The longer the time of exposure to the bleach, the better it's killing cells. The lower the pH, the better the bleach will kill cells. And if there's no organic matter present, the bleach will be effective. The more organic matter that's present, the less the bleach will kill cells. And eventually, if you have a lot of organic matter around, it will it will then activate all the bleach. Any question about that? There are different types of disinfectants, phenol and phenolic, biphenols, which are a little different, biguanides, halogens, alcohols, heavy metals, surfactants, surface active agents, chemical food preservatives, antibiotics, aldehyde, gaseous chemosterilizers, and peroxidizing agents. What did I want to talk about here? I lost it. Generally speaking, these agents are not given to people. You could treat the skin of patients with things like halogens and alcohols, but except for the antibiotics and maybe some food preservatives, patients would not be given these agents internally. Any question about any of that? This is a chemical summary of the different types of agents. And what do I want to talk about? I don't think I want to talk about the table. I'll have you take a look at it. You do not need to memorize this table, but you should know the different categories. Phenol, it's a phenolic compound. Biguanides, like chlorhexidine. Halogens, bleach and iodine are actually halogens. Alcohols, heavy metals. The use of heavy metals has come back into use in medicine. For 20 or 30 years, medicine had stopped using heavy metals because, well, they're somewhat toxic to people and they're not as effective as other antimicrobial agents. However, because of the development of antibiotic-resistant strains, medicine has come back to using heavy metals. And like they'll put it in dressing. Silver nitrate used to be used to prevent gonorrhea in all babies that were born. They treated the baby with silver nitrate to prevent the baby from getting gonorrhea in case the mother was infected with gonorrhea. Nowadays, it's pretty easy to test if the mother is infected with gonorrhea, and if she is, they will give the baby a cesarean birth so that the baby doesn't have to be exposed to gonorrhea. Anyways, that's, I think, how they treat that now. But in the old days, they always treated a baby with silver nitrate. Surface actant agents includes soaps and detergents, and some agents that you can find in the hospital. And I'm trying to remember the name of that. It's not up here. Hexadine, maybe? An antiseptic for the skin, and it's used for treating instruments, utensils, and rubber goods. And then there are chemical food preservatives like organic acids. We add them to things like cheeses, cosmetics, and shampoos, and that's to prevent other bacteria from growing in them. Nitrates and nitrites. I think everybody knows that processed meat like hot dogs, ham, and bacon have nitrates and nitrites in them, and that stops the growth of microbes, or at least slows their growth down. Aldehydes, chemical sterilizers. Let's talk a little bit about chemical sterilizers. One example is ethylene oxide gas. It's very toxic to people, and it's actually very toxic to bacteria too, although endospores are not particularly killed by it. But if you treat bacteria to ethylene oxide gas, the bacteria will die. The trouble with ethylene oxide gas is, like I said, it's very toxic to people, and so it has to be done in a closed environment. Peroxygens and other forms of oxygen killed by oxidation, and this would be things like peroxide and hydrogen peroxide. It's actually one of the few agents which are highly effective on endospores. So endospores are killed by peroxygens. Any question about any of that? Comparing the effectiveness of various antiseptics, they have different effectiveness. Soap and water is not very effective at killing cells. Why we wash our hands with soap and water is you remove most but not all the bacteria from our hands, and it just goes down the sink, and it does not really kill most cells. At 120 seconds, soap and water only kills about 10% of the bacteria on your hands. And then there's different treatments like tincture of zephyrin, and the one that I'm more familiar with is tincture of iodine. That's iodine treatment, like if you have iodine in your, your medicine cabinet, or when they're treating patients in the hospital, it's 1% iodine and 70% ethanol, and they'll treat the skin with this because it's very effective. You reduce the bacteria down to 10% in only 90 seconds of exposure. And of course, when they treat with iodine, at least on the skin, they mark the whole area with the iodine, and then it's there for a long period of time, killing cells. Any question about that? All right, the last thing I want to talk about, I think that's the last thing. I'll talk a little bit more about prions, so maybe not quite the last thing. The second or the third thing from the last thing is I want to talk about some of the microbial characteristics and how they affect the microbial control. This is a simplified hierarchy of the relative resistance of major microbial group to chemical biocides in general. The most resistant microbe to a chemical biocide are prions. Let me blow this up. Prions, well, there's really no chemical agent we can use that will stop prions. Okay? To control prions, you need 1,000 degrees Fahrenheit temperature, or they found that if you treat an agent like a surgical instrument with a proteinase, an enzyme that degrades proteins, that can be used as a treatment for acting against prions. But the point is, prions are the most resistant microbe to all of the chemical agents. Now, prions are not a normal organism because they don't have cells. In fact, all they are is a special protein. Endospores are the next most resistant thing. Endospores of bacteria are highly resistant to almost everything, and they are difficult to kill. Any question about that? Mycobacteria is another bacteria that is resistant to most treatments. Any treatment that is water soluble, so any chemical biocide that dissolves in water, is probably not going to work on mycobacteria. And that's because mycobacteria have a lot of mycolic acid in the cell wall. And mycolic acid is a lipid, and that will prevent the water-soluble chemical from getting into the mycobacteria and then killing it. The cysts of protozoa are the next most resistant microbe. And then we have vegetative protozoa, gram-negative bacteria. They are a little more resistant than gram-positive bacteria because of their outer membrane of the cell wall. It prevents some chemicals from getting into the cell and then killing the cell. Fungi, viruses without envelopes, gram-positive bacteria are one of the easiest bacteria to kill. Water-soluble chemicals can get into the cells, and there's no outer membrane, and then kill the cells. Alcohol, exposure to alcohol will destroy the plasma membrane and denature the proteins, which will inactivate or kill the bacteria. And then the easiest thing of the microbes to kill are viruses with lipid envelope. That lipid envelope is susceptible to damage, and if you damage it, you damage the virus, and then the virus cannot replicate. So viruses with lipids are the easiest thing for a chemical biocide to kill, more so than a virus without an envelope. And what's an example of that? The human cold is pretty difficult to kill because it's well, depending on which one, generally a naked virus. And things like HIV are not so easily transmitted. It is a virus with an envelope, and you need to have direct contact for HIV to move from one patient to another. But this is talking about the bacteria and the microbes in general, you do have to realize that there are exceptions. The mycobacteria are fairly resistant to most chemicals because of their mycolic acid. However, the mycobacteria are very sensitive to killing by alcohol. Alcohol can get through the mycolic acid of the cell wall of the mycobacteria, and they can kill the cells. So alcohol, which we consider a very low, well, we don't even consider it a disinfectant. What do we call it? A blotting agent? No, a degerming agent. That it simply reduces the number of bacteria. Even though it's not a very good, I'm going to use the term disinfectant. In fact, it's a lousy disinfectant. It is good at killing mycobacteria because of the characteristics of mycobacteria, meaning the mycolic acid allows the alcohol to come right through the cells and then kill them. Bacterial endospores are very difficult to kill. Few of the biocides kill endospores, meaning a chemical biocide. However, hydrogen peroxide and the other peroxides are very good at killing endospores. And the peroxides are one of the few chemical agents which do kill endospores. Any question about any of that? I've already talked about envelope viruses and non-envelope viruses. The envelope virus has that envelope which is susceptible to damage, and that's why it is more likely to be killed than a non-envelope virus, which only has a protein coat. And I've kind of already talked about this. Prions are very difficult to kill. Although kill maybe isn't the right word, we'll say inactivate, because all they are is a protein. The problem of how to treat prions has not been completely solved yet. For the British, what they did was they incinerated the cows that had mad cow disease and then killed off the prions or destroyed the prions. For surgical instruments, most surgical instruments cannot be exposed to 1,000 degrees Fahrenheit. That would destroy the instruments if not melt it. And what they do is, I said, they will treat it with the proteinase. And that way, if they're working on someone who may have prions, like engaging in surgery, the instruments will not get prions and then infect another patient. All right, this is our last topic. While microbial control methods are effective, they, especially the biocides, are not uniformly effective against all microbes. So you may have to switch which biocide you're using on which species of microbe. The compounds discussed in this lecture are generally not useful in disease treatment except for the antibiotics we discussed. Any questions about any of that? An example of a biocide which is very effective is bleach. Bleach even kills some endospores, although it does not kill all endospores of all species. It does kill some endospores. And yet, bleach is highly inactivated by organic matter. And so in the hospital setting, almost all of your samples will have organic matter around it. In which case, if you're using bleach, you have to use copious amounts because the organic matter will inactivate the bleach. And bleach is a very good and cheap biocide. Okay? And it's fairly effective. But as I stated, it can be inactivated by organic matter. All right, any questions? If not, we're going to end a little bit early, and I will be at the lab from 6:30 to 6:45 if you have any questions. All right, I will see you later.